This lesson deals with lab number 2, which is Thevenin resistance. Suppose I want to measure the voltage across 2 points in my circuit. So I can think of our circuit as having some Thevenin equivalent with a Thevenin and an Thevenin. And then when I hook up my instrument, it also has a Thevenin equivalent circuit, although we're going to represent it basically just an impedance. Because these two are in series with each other, we form a voltage divider. So V out is equal to Zn over Zn plus Thevenin times Thevenin. I'd like my instrument not to affect my circuit. In other words, when I measure something, I don't want to change what's actually present here. One way to do that is to make Zn much greater than Thevenin, so I could throw that term away. So the Zn's cancel, and I get that V out is equal to Thevenin. So what types of Zn's do we have for our instruments? Let's take a look at the oscilloscope. The input impedance of the oscilloscope depends on what kind of mode you're operating in. And there's 2 modes, a DC mode and an AC mode. In this experiment, we're going to take a look at a DC mode, which stands for direct coupling. In other words, we're just going to connect this directly to our circuit. The equivalent circuit of our analog discovery is approximately a resistor of 1 megohm in parallel with a capacitance around 24 picofarads. The capacitor's impedance changes with frequency. Let's take a look at the range of frequencies before this capacitor begins to affect this resistance in total impedance. We'll take a look at that on the next page. As you recall from ECE 202, the impedance of a capacitor is 1 over j omega c. The magnitude is just 1 over omega times c. For our Cn of our oscilloscope, this would be the impedance of the capacitor, which is in parallel with the 1 megohm resistor. Now for very low frequencies, this becomes a very, very large number, and the parallel combination is just the 1 megohm. But as frequency increases, this begins to decrease. Total input impedance is going to be a function of frequency. The largest value it's going to be is 1 million ohms. The smallest value could actually be 0. And what frequency does this begin to happen at? Well, if I take this impedance and set it equal to the 1 megohm that I have, I could solve for the frequency where those two have the same value. Let's solve this equation. So I'm going to bring the Rn over here and bring the omega over here. So omega is equal to 1 over Rn Cn. Divide by 2 pi and you have the value of frequency. So for a 1 megohm resistance and a 24 picofarad capacitance, we're looking at about 6.631 kilohertz. In other words, for frequencies less than that, the input impedance is just that of the resistor. For frequencies above this, it begins to decrease. Now, that doesn't mean that we still can't use our oscilloscope at frequencies above this, but for frequencies above this, our equivalent impedance is beginning to decrease. So it would depend on the value of the Thevenin resistance looking back into our circuit if we form a large voltage divider or not. Now, what's the input impedance of our digital multimeter? The input impedance of our digital multimeter also depends on what mode it's hooked up in. There's a DC mode and AC mode. In the DC mode, usually referred to as direct current, we have the following equivalent circuit. Again, similar to our oscilloscope. But now Rin is much, much larger. It's about 10 million ohms. And the capacitance in the manual says it's less than 100 picofarads. I measured around 30 picofarads using a LCR meter. So here too, we've got an effective impedance that's changing with frequency, but it is a larger impedance, and so we can have less of a loading effect. Let's take a look at some of the equivalent circuits of our function generator and some of the things we're going to be measuring in lab. In the last lab, we used a function generator, and it too has a Thevenin equivalent circuit, where we've got an AC term and a DC term. The AC term we saw we could generate sine waves, square waves, ramps, triangle waves, and many different types of wave shapes. There's also a DC level that we can adjust. We normally set it equal to 0, but you can have a level in there that's positive or negative. And lastly, there's a Thevenin resistance associated with our function generator, and we're able to set its value to 0 or 50 ohms. The reason we're going to set it to 50 ohms is that when you terminate a transmission line in its what's called characteristic impedance, if that also matches the impedance of the source, then you get no reflections on the line. We'll look at this in some later courses. In this lab, we'll take a look at finding the Thevenin resistance of several different types of circuits, and one of which is a battery. If you were to physically cut open a battery, you wouldn't see a resistor inside of it, but you see its effects at the terminals. In other words, the most current that you can draw out of this battery is if there was a short circuit here, and that would be V sub S divided by R sub S. So R sub S really is an indicator of how much current you can draw from a battery. Now the value of this resistance depends on the kind of battery that you have, the size of it. Usually the bigger it is, the smaller the value of R sub S is. So for an alkaline battery, a D-type cell, the value of the Thevenin voltage we'll call V sub S is about 1.6 volts, even though it's called a 1.5 volt battery. For that type of a cell, that's roughly its fully charged voltage. And the resistance is about 100 milliohms. But as the battery gets smaller, the value of the resistance gets larger. We don't have as many paths for current to flow. We're going to measure a 9 volt battery in this experiment, and its fully charged voltage is about 9.1 volts, and the Thevenin resistance is around 2 ohms. What's also interesting about the Thevenin resistance is it's very temperature dependent. So as the temperature goes down, typically this goes up, and that means you can't draw as much current. So in a car battery, problems with starting it is usually in cold environments. When you have a very cold morning, this resistance, if it's higher, you can't draw as much current to start the automobile. Also, as the battery begins to age, the value of this resistance actually begins to go up too, and the value of this begins to go down. We'll talk some more about that in the experiment. We're also going to try to find the Thevenin resistance of a microphone. And there's different types of microphones. We're going to use a dynamic microphone in lab. And the Thevenin resistance is somewhere between 30 and 1,000 ohms, depending on the particular microphone. Now, the Thevenin voltage for a dynamic microphone, as you speak into it, is on the order of about 100 microvolts, peak to peak. So not very big. We're going to need an amplifier to make it larger. And we're going to use an op-amp to do that in a later experiment. There's also other types of microphones, one of which is called a crystal microphone. And this uses a piezoelectric piece of material, and it's able to generate very large voltages, in fact, significantly larger than we had with our dynamic microphone. So it can pick up sounds that are very far away. This would be the kind of microphone you'd be using maybe in a stadium trying to pick up some conversations in a huddle. But the amount of current that you can draw out of the microphone really depends on how much energy you've put into it. When you have a larger voltage, you'll have a much higher Thevenin resistance because you can't draw a lot of current from the microphone because you're just getting a sound pressure wave. Thevenin resistance for a crystal microphone is quite high. We have to worry then about input impedances of our circuit when we interconnect the microphone with, say, our amplifier. We're going to look at this in a later experiment. Let's next take a look at measuring Thevenin resistance. Suppose we want to measure the resistance of our battery. So here we got the terminals of our battery, and it has a Thevenin equivalent circuit. Now, when you hook up the multimeter here, it's going to apply a current and then measure the voltage across the terminals. But this voltage being present is going to change the voltage that's here. So we're going to get a false reading on our multimeter if we were just to hook it across here and measure the resistance. You could also burn out the multimeter because we can be pumping current in depending on the size of this voltage. So we don't want to do that. Just use the multimeter to measure resistance when the resistance is outside of the circuit, not in a circuit that's active. So how can we measure effectively this resistance? Well, we have two unknowns here. We have V sub S and R sub S. We create two equations. We can then solve for the value of either. What we're most interested in is the value of R sub S. Let's do the following. Let's hook up a load across the circuit we're trying to determine the Thevenin resistance of. But before we do that, let's measure this resistance with our digital multimeter. Then we hook this up, and we can measure this voltage with our meter, and then we can calculate the current if we know the value of resistance. We could also use the meter in a current mode, but there's also a resistance associated with it, and it has a bigger loading effect when you change the scale. So I'll tend to try to measure voltages across resistances and then use that to calculate the current. So measure this resistance, hook it up in this circuit, and then measure the value of voltage, which will give us the current. If we go around the loop here, then the rise in voltage would equal the drops, which would be this current, I'll call it I sub RL1, times R sub S, plus the voltage across R sub L. So here I've got a one equation and two unknowns. I don't know the value of V sub S or R sub S, but I do know the value of the current and the voltage in this circuit. I'll do that with a second value of resistance. So put a different resistor here, measure its value before you hook it up, and then measure the voltage, and then calculate the current. So again, the rise in voltage equals the drops around the loop, which would be this current I sub RL2 times R sub S plus the voltage across here, or we could take the current times the resistance, but we already know the value of voltage. So again, here's a second equation in the two unknowns, V sub S and R sub S, which are our Thevenin equivalents. Let's solve these two equations. So we had two equations and two unknowns, but we had V sub S on the left-hand side of the equation. If I equate the two equations, I can eliminate V sub S, and now I can solve for R sub S. So here's R sub S times the current I sub RL1, and here's the value of R sub S again, but now with the other current I sub RL2, and I'll bring it on this side of the equation with a minus sign. Now let's put this on the other side over here, so then I've got the difference of these two voltages. Then I can solve for R sub S as this voltage divided by this current. So here's this term, and here's that current over here. What I did was I put a minus sign through, and so I made this term negative and this term positive. Here I've got the two measurements together, and these two measurements together. I can calculate the effective value of R sub S by taking the difference of the voltages for the two different loads, and then also the difference of the currents. Now in ECE 201 we introduced switches, and we'll take a look at some of the properties of switches. Toggle switch is just that, it toggles between two different positions. Now with switches we have two terms that are called poles and throws. The arm, or the part of the switch that is moved to open and close a circuit, is called a pole, and the throw is the number of circuits that it connects. That's kind of a formal definition, but let me show you a picture. It might be a little bit easier to explain. So here's a single pole, single throw switch, and here's my pole. I'm going to take that and go from an open to a short. So I'm going to be connecting up one circuit with the action of throwing the switch. So here's the pole, and then the throw is just connecting up one circuit. Now if I were connecting up two circuits, this would be the configuration with a single pole but a double throw. This is similar to a three-way switch in your house if you have two switches at two different sides of the room to turn the lights on and off. A lot of times we want to control two circuits with one switch, and here's an example of a double pole but a single throw. So we're controlling one circuit with this switch, one circuit with this switch. Here would be a double pole, double throw. Here's two circuits that are controlled by these switches being changed in state from here to here and from here to here. Last, let's take a look at the board we're going to be building our circuits on. It's on the next page. In lab, we're going to be building our circuits on a solderless board, which allow us to be able to build and modify circuits very quickly without having to solder components together on a printed circuit board and not be able to modify things. Although we're going to take a look at soldering in a later experiment. This particular solderless board was introduced in the 1970s by a company, and they called it a proto board. And so some always refer to a solderless board as a proto board, but that's actually a brand name. And in the lab, I'll just refer to it as a solderless board. There's a series of holes here that are connected in strips, and take a look at what those strips might mean. Let me zoom in on this a little bit. There's a channel here separating this set of rows from this one. It's actually the width of an integrated circuit. We're going to plug op amps in it a little later in the course. These 5 holes are all shorted together. These 5 holes are all shorted together. So are these, so are these, and so are these. In other words, you can put a resistor, say here, and then hook up the other end of the resistor here, and now you can make some connections to it. Let me show you an example. So as I put a resistor in this hole, and take the other end over here. Now I can put 4 more things into here. They'll hook up to this resistor, and likewise over here. A lot of these rows here, they're short rows with 5 things connected together, and some with some spring clips, so it makes a nice firm connection to the wires that we're sticking in here. Now sometimes you need more than 4 connections to an element, and that's what these rows on the top are. So here's a set of 5, 10, 15, 20, 25, 30, 35, 40, 45, 50 holes, all shorted together. So maybe put your positive power supply here, and you make a lot of connections to it. Then the row above it is not connected to it, but these are also 50 holes that are shorted together. And there's another set down here of 2. So it gives a lot of options for building circuits and putting them together. The purpose of this lab is to look at techniques for measuring the Thevenin resistance. We're going to use a solderless board for quick assembly and disassembly of circuits without a need to solder wires. The concepts that we covered in the lab lecture, and we'll see also in the lab, is the accuracy of the analog discovery, measuring source resistance in linear circuits, pulls and throws of switches, battery performance and characterization, and lastly, microphone characterization. Also learning some new laboratory techniques, and one is the hardware settings on the function generator to change its output resistance, hardware settings for the scopes coupling of AC and DC, and lastly, we'll learn how to measure a DC voltage with the DC multimeter. And this is lab number 2.